So for the first question, suppose T maps the real numbers to the real numbers is a linear transformation. Is T diagonalizable? Well, if we look at this, with a linear transformation, it has to satisfy our properties. And if we look at the eigenvalues and eigenvectors, if we say that we have T of 1 equals 4, well, then T of 1 equals 4 times 1. And that 1 can be used as the base vector. Because it has to satisfy our addition and scalar multiplication, we can see that T minus 4I V is going to equal 0. So it has an eigenvector, and that eigenvector is 1, or any number in this case. And that vector makes up a basis because we just need a real number to form a basis for R. So yes, T is diagonalizable. How could we extend this? Well, we could do R2 to R2. We could do R3 to R3. We could do C2 to C2, so on and so forth. But if we're going from R to R, we are diagonalizable. And for each different type of domain and range that we change to, we could have different answers, yes or no. Now we're looking at A2, where V is a vector space, T mapping V to V, and is a linear transformation. T has two distinct eigenvalues and is not diagonalizable. What is the minimum dimension? Well, in order to have two distinct eigenvalues, we need to have x minus lambda 1 times x minus lambda 2 is our characteristic polynomial. But if we have this is a product of distinct linear factors, where a polynomial can factor into distinct roots. And we showed that if the characteristic polynomial factored into distinct roots, then we would be diagonalizable. So at least one of these roots has to be non-zero, or we need to have some other expression we're multiplying here that isn't reducible into linear factors. But we see that here we would have 3. This would be a total of dimension of 3. Whereas if we multiplied by some other factor that wasn't, we couldn't divide or factor into linear factors, it'd be degree 4. And the degree of our characteristic polynomial is the dimension of V. So here, the minimum dimension for V is 3. Now for A3, we have two subspaces of a finite dimensional subspace. Now it's asking, are there intersection? True or false? The intersection is the empty set. Well, if we look at two subspaces, both subspace 0 is in W1 and 0 is in W2. Well, thus 0 is in the intersection, so the intersection so 0 must be in the intersection of W1 with W2, so it's not the empty set, so this is false. This finite dimensional subspaces isn't really needed, it's kind of a red herring. Okay. Now we have the derivative operator, and we want to look at the kernel of the derivative operator. So we're saying that P of x is in the polynomials of degree n of R, and the derivative applied to P of x equals 0. Well, if we think of all the things that can go to 0, the derivative of a constant equals 0. So it's anything times the constant. So it is the set of f of x in Pn of x, Pn of R, real polynomials, such that f of x is equal to some constant where the constant is in R, or it's just our constant polynomials. And provide a matrix representation of a non-diagonalizable singular matrix that has an eigenvalue 1. So when doing this, the easiest thing to do is to have an upper triangular matrix, because the upper triangular matrix, the eigenvalues lie on the diagonal entries. So I'm going to have an eigenvalue 1, and singular matrix means that lambda equals 0 is an eigenvalue. So I also need 0, and I need to be non-singular or non-diagonalizable. So the easiest way is to have something kind of like this, where we have this 0, 0 block. And if we remember, we had 0, B, 0, 0, or A, B, A, 0. And we said that if B did not equal 0, we weren't diagonalizable. We put that inside here, we can have a non-diagonal matrix. So we're going to have the matrix 1, 0, 0, 0, 0, 1, 0, 0, 0. And now we're singular because we have a diagonal entry that's 0. We're non-diagonalizable because we have this little block thing. And then we have a 1 up here, meaning we have an eigenvalue 1. There are many solutions for this question. Now we want to construct a matrix representation of a linear transformation such that it has no eigenvalues. But when we square it, we have an eigenvalue with algebraic multiplicity 2. So what I need is I need t squared to have some sort of xy, to have some sort of nice properties with the eigenvalues both being real. And the one thing here with the hint, it says think rotation matrices. Well, if r theta, if t equals r theta, then t squared equals r 2 theta. Because we showed that r theta of r phi of xy equaled r theta plus phi of xy. You add those angles together. So we're going to do 2 theta. And if we think about this, we have 2 angles. We have to somehow get either a real number. We can either be here or here when we're squared, but we can't be real for t. So here, this, if I take 1/2 of my angle, whatever my angle is, I'm either going to be here or I'm going to be here, meaning half my original angle, whatever it is also going to be a real value. So that allows me to eliminate, this value as a reasonable value. So that means that I can now just consider this as my eigenvalue. My eigenvalue is -1. And the rotation matrices we showed in the assignment will have complex conjugate eigenvalues. So if we look at what can, when I double the angle, makes 1, I've got this vector here, which the eigenvalue here would be I, and the complex conjugate would be -I. And if I take this 3/4 angle and I double it, I'm going to get all the way to -1 again. So we can see that if I have I and -I, that's going to be the appropriate linear transformation. But now, what gives me this half angle? Well, that's pi by 2 is going to be my theta. or I should say theta equals pi by 2. So if theta equals pi by 2, then I'm going to be, well, what's cos of pi by 2? What's sine of pi by 2? And it's going to, cos of pi by 2 is going to be 0, and sine of pi by 2 is going to be 1. So it's going to be 0 minus 1, 1, 0. This is going to be the matrix representation of my linear transformation, which is what we were asked for. We were asked for the matrix representation. If we wanted to know what t of xy was, well, here t of xy would equal minus y x. Note that you could also have the matrix representation 0, 1, minus 1, 0, because you could do this equals 3 pi.